Fine-tuning and reinforcement learning are the real heroes behind Claude, Gemini, and Grok. Without them, you'd have a super smart search engine, but not a helpful assistant. With them, you unlock reasoning, instruct following, tool you, and the ability to refuse harmful or incorrect requests. So in this video, I'm going to walk you through how that transformation actually happens. How does a model go from raw prediction to something that behaves like a tutor or an analyst or a collaborator? But before we get to fine-tuning and reinforcement learning, we need to zoom all the way out, because none of the post-training magic makes sense until you see the full cycle of an LLM. Large language models don't go straight from blank state to helpful assistant. They go through distinct stages, and each stage gives them a different capability. Pre-training is stage 1, and this is where the model gets its raw intelligence. It's also the longest and the most expensive phase. It often takes months of compute and millions of dollars. During pre-training, the model has exactly one job, and it is to predict the next token, word by word or subword by subword, across massive internet scale. So the simple objective, repeated trillions and trillions of times, builds a huge amount of world knowledge. So let's take an example. Look at the image right here. When it sees the sky is, blue becomes highly probable, while words like clear, dark, and orange are less likely. Take, for example, the sentence, the sun is setting, the sky is. Suddenly, the orange token is more likely than blue because of the context before it. So just through next token prediction, we pick up patterns like the sky is blue, sunsets are orange, and many thousands of similar relationships. So at this stage, the model really starts from random weights, so the outputs at the beginning, they're nonsense. The training is massively expensive, and the result is a base model that knows a whole lot and is a solid prior, but doesn't yet know how to behave like an assistant. So this is raw intelligence, but not the shaped behavior that we ultimately want. Then you have mid-training, which you can think of as continued pre-training, but on very carefully chosen data. So the objective stays the same. We're still trying to predict the next token. We're still learning pattern frequency, but now the data is targeted to be refined and to extend capabilities. So the goals include, in this stage, introducing new languages, Chinese or other languages, to add new modalities like images and audio, or to expand the context length so that the model can process much longer sequences. By the end of the mid-training, the model has broader knowledge and can understand multiple modalities and can handle long-range contexts. However, it's still a next token predictor. So there's no concept of let's be helpful or be safe or act like a tutor. So the key insight here is that mid-training sharpens the understanding, but it doesn't teach behavior. So for that, we finally get to post-training. That's the part where we actually teach the behavior, and that's where the model becomes actually useful. And there's 2 techniques to do that, which is the point of this video. Let's look at the first major technique. Fine-tuning exposes the model to high-quality instruction-response pairs. It teaches how to follow instructions, how to structure an answer, how to sound like a tutor, a guide, or a helper. Fine-tuning is about competence, right? So show the model examples. Here's how to behave, here's how to format, here's how to respond, like in this example right here. The other technique, reinforcement learning, is where the model gets feedback on which answers are more helpful, which ones are safer or more aligned or better reasoned. This is about judgment, not content. So this is where the model learns what's preferred and what should be avoided. Later on, you'll see that when you put supervised fine-tuning and reinforcement learning together, you get the moment where a model shifts from a smart statistics engine to an assistant with reasoning and judgment. So let's recap. Pre-training, the model reads the entire internet without supervision. It gains raw information, general knowledge. Mid-training, the model reads targeted, advanced books, and it's more refined. Post-training, the model learns how to be a teacher or an assistant, and it applies the knowledge interactively and responsibly. Right. Fine-tuning and RL each play very different roles when it comes to shaping a model's behavior. So to make that intuitive, let's start with a very simple analogy to capture the contrast. Fine-tuning is like standing next to grandma in the kitchen and trying to copy every move she makes. Every stir, every pinch of salt, every step in the exact order she does it. The model is judged on how faithfully it's able to reproduce the sequence of steps. Okay, the emphasis on the sequence. Did you follow the steps of the recipe? Did you perform the steps in the right order? How does the final dish look like? So, because of that, we rely on high quality labeled data. Every step in the sequence needs to be really high quality. The way we train in this method has to be predictable and stable, and we have a rich ecosystem for that. We have LoRa adapters, we have PEFT, so on and so forth. And you can run it on a handful of GPUs. The limit is that you're limited to what the data set is going to show you. So you're as good as the data. So the better the data, the better the training is going to be. And you're also limited because you're not going to invent new ways that you've never explored. So you're not going to have new approaches. So you're trying to imitate. You're not trying to be original or creative. So fine-tuning gives you the competence, right? Structured, reliable, rule-following behavior drawn from examples. Reinforcement learning, on the other hand, takes a completely different approach. So instead of copying grandma step by step, the model is free to cook however it wants as long as the final dish tastes really good. So we're looking at the final output. You're no longer grading the process, you're grading the outcome. How good was the final answer? And the signal it learns from, it's not the answer, it's more of the way you grade the answer. So RL lets the model stumble into new and unexpected strategies. And it's the technique you reach for when you want the model to internalize human judgment, not just mimic the data. However, RL has its own set of headaches. You need really strong graders. They have to be, but the graders can be biased or exploitable or hackable. So whichever you think the grader is going to give you a good score, you optimize for that, even if it doesn't make sense. So this is what we mean reward hack. In RL, the train loop can also be unstable and very computationally expensive. So these are downsides of reinforcement learning. So fine-tuning gives you competence, RL gives you alignment, the ability to be helpful, safe, natural, more aligned to something that gets a higher reward, or that the grader deemed to be higher reward. So most frontier labs follow the same overall sequence when it comes to the training pipeline. They start from a base model, they apply fine-tuning to teach the structure, obedience, core behaviors, and then you apply the RL to refine the helpfulness or to align to human values. And this pipeline turns a raw knowledge into a usable assistant. Let's zoom in on how fine-tuning actually works under the hood. So there is one principle that sits at the heart of fine-tuning. The model does not learn what you intend or what you hoped it would infer. They learn whatever you represent. So you're as good as the data. So in other words, the model, it only absorbs the behavior that are explicitly shown in the data. So every token in the data set becomes a teaching signal. Your schema in the data set is going to teach the structure, how a conversation looks like. If you wanted to teach how to think through a problem, your data set needs to have reasoning in the inputs. If you want to teach it skepticism, you have to show it counterfactual information. So it's going to learn when to question the context. If you want to teach the model how to say no, you need to put refusals to teach boundaries. If you want the model to decide which behaviors matter the most, then your sampling strategy teaches priorities. So in fine-tuning, what you're supervising on is the process, not the answer. So the data itself becomes the product. You're not merely feeding it questions and answer pairs. You're teaching in the entire grammar of a conversation. Who is speaking, who's listening, what role the model is supposed to play. So the better the data, the better the training. So that's why when OpenAI trained ChatGPT 3.5, they didn't dump untagged Q&A lines into the model. They actually structured it. They put user tags and assistant tags next to each of the sentences. So these tags do far more than label terms. They anchor identity. So without them, the model starts mixing up who is who, might answer its own questions. So the whole multi-turn dialogue collapses. So if you want the model to hold that structure, to have coherent conversation, you have to show that structure in your schema. Here's another core principle to keep in mind. You have to reward the reasoning path, not just the final answer. For example, the math model Minerva wasn't trained only on question-answer pairs, it was trained on chain of thought traces. Take a look at this example here where we show the intermediary step before reaching the answer. So when you show the model the intermediary steps for the reasoning, it actually is 30 to 50% more accurate on unseen problems. Why? Because it's not just memorizing the final output, they learn the process that gets you there. Same thing, there's a healthcare chatbot that was once trained on data that included internal tags of file names. So when it was deployed, it started to leak those file names back to the user. So the model had no concept that this is metadata, don't say it. It simply reproduced whatever it saw during the training. So the lesson here is to supervise the reasoning you want, but keep the scaffolding private. Teach the model how to think and then strip out anything you don't want echoed in production. What about making your model more robust to retrieval errors? So one of the most overlooked parts of post-training. And the idea here is simple. You have to fine-tune the model to recognize and recover from bad context. So imagine your legal assistant retrieves a document claiming the Supreme Court of Canada is in Montreal. If your model has only seen correct documents during the training, it will just confidently parrot the mistake because statistically, whatever is retrieved is right. But if you show counterfactual examples like the user saying, where's the Supreme Court of Canada located? And then in the output, you put the document is incorrect, the Supreme Court is in Ottawa. Then you're teaching the model to be selective about skepticism. It learns to check consistency instead of blindly trusting whatever the text shows up in context. So this reduces hallucination by simply injecting refutation examples into its fine-tuning mix. So here's the important thing to learn. If you only show it perfect documents where everything is correct, the model never learns to doubt. You need to put counter examples to teach the model when it is that it can push back. The same thing with safety and scope limits. They don't just magically happen. They are learned through the patterns you embed in the training data. So take Amazon Shopping Assistant, for example. The moment it launched, user immediately pushed it outside of its domain. They start to ask to write code, tell a joke, or whatever. The earlier versions of this, they tried to oblige, not because they were rebellious, but because they had never been shown what their scope actually was. So what's the fix? Amazon added fine-tuning examples that explicitly demonstrated what is the assistant allowed to do and what is not allowed to do. So whenever the user asks it for something outside of its boundaries, now the model learned its limits, because those limits were represented in the data. Finally, here's one of the most important but least understood examples. 100 million well-balanced examples, they beat 1 billion uncurated examples. So it's more about the quality of the data than the quantity. For example, Llama 2 Chat, Meta's biggest performance gains came not from scale but from data mixture tuning. A 3% increase in safety examples reduced harmful outputs by 80%, according to the Red Team benchmarks. So it wasn't about bigger data set, it was better So what about the other strategy just to add more data? So there's a team that actually tried that and they've added 5 times more data, but keeping the same mixture ratios. And what's the result? Worse performance. So the lesson is simple, but easy to get wrong. It's not about bigger data set, it's about better balanced data set. So you need to curate for the behaviors you actually want, not just the ones that are easy to scrape. Now that we've seen what reinforcement learning does, let's talk about how you make it work. Because RL isn't about showing the model how to reason step by step. That was the job of fine-tuning. RL is about building a strong grader and letting the model optimize against it. And here's the catch. In the real world, every reward becomes an incentive, and the model will follow it perfectly even when you wish it wouldn't. So let's walk through the principles that keep RL grounded and aligned. So here's a guiding principle. You want to automate anything that can be objectively verified and learn everything that can't. So on the deterministic side, where things are clean and crisp and fully automatable, like in, for example, programmatic checks, in a code generation example, a Python unit test is the perfect judge. It doesn't care how great your answer is, it just cares whether the method actually prints the right numbers. Or you can have regex. For an SQL query, for example, you can enforce that the output forms a valid select from where pattern and that it parses without error. So it's as simple just a pass or fail. These deterministic graders are rock solid. So they're reproducible, they're immune to hacks. But then there's the other category, the things you simply can't check with rules. So these are learned graders. So for example, customer support models. You can't easily match with a regex things like empathy or politeness. So you train a reward model on thousands of labeled conversations that encode helpfulness, tone, and politeness. And because those subjective graders, they drift over time, you need to continually audit them. So real humans rescore random samples to make sure the grader hasn't started over-rewarding overly sweet, chirpy responses. Next, you want to anticipate reward hacking. So if you reward only one thing, the model is going to laser focus onto that metric and contort the behavior to game it. So this is a real example. A bank once experimented with a chatbot rewarded purely for enthusiasm. And so within a week, the model opened every conversation with hello, because that was the shortest path to the perfect score. And it repeated that word, hello, 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 because that is what led to the perfect score. So the fix was to add a multi-term reward that balanced helpfulness, brevity, non-repetition, penalized emoji overuse. So you kind of want to design a reward function in a way like the tax law, not like a wish list. Like assume the model will find loopholes and design incentives so you're already one step ahead. Here's another principle that a lot of teams underestimate. So reinforcement learning is only as good as the world or the environment it is trained in. So if your training environment is too clean, too perfect, too frictionless, the model develops habits that are different than what's in reality. For example, tool use, LLMs. Say your agent can call a calculator or search an API. If your training environment never simulates latency, rate limits, or occasional 404, then the model will happily spam those tools 10 times per query. It never learns restraints because there's no cost, no penalty, no downside. So the fix, in an actual environment, you want to inject latency. You want to inject stochastic failures. You want to inject rate limits into the training loop so that the model learns to retry gracefully instead of hammering the tools like a denial of service bot. One startup actually ran RLHF using live external APIs, all in parallel, and their model generated such a massive burst of traffic that it got itself rate limited and temporarily blacklisted. So the way they fixed it is by switching to mock services, and they throttled training environments that behaved more like in the real world. So the takeaway here is that you want to train your model in an environment that reflects the friction that you have in the real world. You have timeouts, errors, cost, not in a fantasy world. Here's another big lesson in RL that people often missed. So coverage and mixture matter more than single reward purity. What does this mean? So picture an enterprise assistant trained across 4 different RL environments. You have one for math problem solving, one for code debugging, where the reward is to compile successfully, one for customer support chat, where the reward is to check on the tone and politeness, or an environment on retrieval QA is where the reward is based on the factual correctness. If you oversample debugging, for example, the model gradually forgets how to be polite. If you oversample on the tone, its factual grounding weakens. So one domain gets too loud and everything else starts to drift. The solution here is to have a mixture of environment scheduling. So what does this mean? That means that for each training batch, pull proportionally from all environments. And then you track the per domain reward curves to catch early signs of catastrophic forgetting. So here's an analogy. It's like going to the gym. If you only train your arms, your legs, they're going to weaken. So a healthy model needs like cross-training across the whole different muscles in the body. So cross-training across reasoning, style, factual grounding. Never let a single reward dominate the gradient. So reinforcement learning thrives on diversity. Here's one last thing to make RL work in the real world. Reinforcement learning is not trained once and deployed. It's like a living feedback system. So in practice, the loop looks like this. The model generates fresh rollouts. So these are inferences, conversations, summaries, tool calls. These outputs get graded automatically. You cluster the failures. You want to detect failure patterns like jailbreaks, hallucinations, bad tool calls, sloppy reasoning. Those failures become negative examples folded into the next training batch. You retrain, reevaluate, and start the loop again. This is exactly what frontier labs do. So OpenAI, Anthropic, and DeepMind, they continuously refresh their red team sets with new jailbreak tricks and emerging reasoning edge cases, and then they periodically run reinforcement learning or DPO to harden their models. If you don't run this loop, the model is going to drift because user behavior evolves, attack patterns evolve, the world evolves. So having a model that's robust is not a one-off thing. It's an ongoing training system. So here's the cycle. You roll things out, you infer, you grade, you put a reward, you batch the negatives, you retrain to keep the model aligned to the current reality. So frontier labs don't just train, supervise fine-tuning or RLHF once and ship the model. They run alternating cycle chaining. So it goes fine-tuning, FT, then goes back to FT, then back to RL. Each round produces a slightly better model, and that model becomes the engine that generates higher quality data for the next round. It's kind of a bootstrapping. DeepSeek, R1, Qwen, and Llama all iterate through multiple cycles. Each cycle refines both the policy and the data set. And the process steadily builds richer reasoning traces and cleaner preference labels. So let's see an example. DeepSeek R1 fine-tuned on early reasoning traces. ran RL to improve the reasoning, used the improved model to generate better reasoning traces, and train a model, fine-tune a model on those reasoning traces, and then just repeated the loop, is the same self-improving dynamic in that AlphaGo used in the self-play. But this one is applied to language and reasoning instead of board games. One of the biggest breakthroughs in modern post-training is this. Synthetic data generation is the new scaling engine. So instead of relying only on humans, a model uses its previous checkpoint to do a bunch of things. First, it's going to generate candidate answers, reasoning traces. It's going to score them, filter out the weak samples, and feed the best ones back into SFT. This approach, often called projection sampling or self-curation, lets the model essentially teach itself by iterating on its strongest outputs. For example, both OpenAI and Anthropic rely heavily on model-graded pipelines. So the reward model itself scores completion before they're allowed into the next fine-tuning dataset. So here's an important point. The reward model is not just a helper. It's kind of a quality control valve. It plays several roles. It scores the RL rollout. It ranks those rollouts and creates which outputs get added back to the SFT dataset. So if your reward is miscalibrated, it weakens the whole thing. It triggers model collapse, where the policy over-optimizes for a very narrow reward signal and stops behaving more broadly and naturally. For example, in the Llama post-training, the same reward model is used for both DPO training and filtering synthetic data. So it keeps the supervision aligned with the scoring function. So at every stage that the model goes through, it inherits the biases of the reward model of the stage before. So if one of those stages drifts, then everything drifts even more. Here's another point to mention. When a powerful base model becomes open source, fascinating things happen. So post-training becomes decentralized. For example, Llama 3, when it arrived, hundreds of forks appeared. So each fine-tuned for different things. One for coding, one for legal reasoning, one for medicine, one for long context tasks, tool use, and so on and so forth. So now you have a distributed research network where thousands of variants explore new mixtures, new RL setups, new domain specialization. So all of these are created through community-led post-training loops. So whenever you make something open, it produces diversity that centralized labs can't match. So when you bring things to the community, it scales naturally. Lastly, deployment is not the finish line. It's just the beginning of continual alignment. Labs and open source communities refine those deployed models through many rounds of fine-tuning on new user feedback or RL on emerging reasoning patterns or new updates based on safety issues or changing user behavior. So this pushes the field towards online alignment. So models that evolve as the world evolves. So things will always happen in a loop. So what I'm trying to explain here is that post-training, it becomes like an ongoing conversation between the lab and the world, between the users and the model. You pre-train, you post-train, you deploy, you observe, and then you post-train again. Thanks for watching.